Hello, so in this video, we're going to look at how we can combine partial fractions and binomial expansion into one question. So this is an example of a question here where we're going to need our knowledge of partial fractions and binomial expansion. So we've got to show that this fraction here, 1 over 2x plus 1 times 1 minus 3x, can be approximated by the expression a plus bx plus cx squared plus dot dot dot, so an infinite series where a, b, and c are real numbers. Also, there's like a second part of this question as well. So also we've got to state the values of x for which this approximation is going to be valid. So we want to approximate this fraction here for certain values of x in this form a plus bx plus c x squared, and we want to state the values of x for which this is valid for. Okay, so what we need to do then is actually the objective is to write this fraction as the sum of two binomial expansions. That's kind of the idea of what we want to do. So let's just write this down here. So idea, write fraction. Just want to write fraction as the sum. So as sum of two binomial expansions. So binomial expansions. Okay, so that's what we're going to do. So yeah, let's go to the next page. So we're going to use partial fractions to break this up. So we know from our partial fractions knowledge, as we looked at in previous videos, that if you've got 1 over the product of two linear factors, you can write it like this. So a constant over that linear factor plus another constant over that linear factor. So if we times both sides of this equation by that denominator, we get 1 equals this thing here. And then if we expand the brackets like I've done there and there and there and there, we would get a and then minus 3ax plus 2bx plus 3b. So we can see if we just factorize out our terms, we would get minus 3a. So I'll write this again, minus 3a plus 3b lots of x plus that should be a 2b there, sorry, my bad. 2b lots of x, and then a plus 3b there. So we can see by matching up our coefficients, again, let me just write that 3 a bit nicer. By matching up the coefficients, we've got a number 1 there, and then we've got a 0x there. So that tells us two things. So it tells us that 0 is going to be equal to this minus 3a plus 2b. So let's just write this here. So the 0, equation number 1, 0 equals minus 3a plus 2b. And equation number 2 is that this number 1 constant is equal to a plus 3b. So we know, therefore, that this a value must be equal to 1 minus 3b from this second equation. So we can plug this into the first one. So therefore, we get 0 equals minus 3 times a, which is the same as 1 minus 3b, which we just determined, plus 2b at the end there. Again, if I just make the writing smaller. So what we get, therefore, is we get that, yeah, so 0 is equal to minus 3 plus 9b plus 2b. When we expand those brackets there, that's going to give us minus 3 plus 11b. So therefore, we get that b is equal to 3 over 11. So we get b is 3 over 11. And so therefore, a is going to be 1 minus 3b, which is going to be 1. Well, the number 1 is just 11 over 11. Take away 3 times 3 over 11. So 3 times 3 is 9. So 9 over 11. You will therefore get 2 over 11. So a is going to be 2 over 11. So therefore, our partial fractions are going to be a, which is 2 over 11 times 2x plus 3, in addition to 3 over 11 times 2x. 1 minus 3x there. So 1 minus 3x, and that would be our expansion for this expansion. Yeah, so we get this result there. So next step is to rewrite our result. So we got this result here when we use partial fractions. So we got a result of 2 over 11 times 2x plus 3, in addition to 3 over 11 times this 1 minus 3x. That's what we got when we did partial fractions. So we can actually rewrite this. We can rewrite it like this. So we can rewrite it as 2 over 11 times by 2x plus 3 to the power of minus 1. And we can write this next bit as 3 over 11 times 1 minus 3x to the power of minus 1. So we're just rewriting the way that we're laying this out basically, because obviously 1 over x is the same as the same as x to the power minus 1. So 1 over 2x plus 3 is the same as 2x plus 3 to the power minus 1. So we're rewriting it like this. So now then our next step is to actually do the binomial expansion. So step 3, do the binomial expansions, because we actually got 2 to do. So do the binomial expansions. Okay, so then let's start with our first one here. So this 2x plus 3 to the power of minus 1. So 2x plus 3 to the power of minus 1. So remember, we can write it like this. This is the same as 3 plus 2x to the power of minus 1. So yeah, we get this. We can now factor out, we've got to factor out this 3 in order to use our formula. So factor out the 3, we get 3 times 1 plus 2 over 3x, and that's all to the power minus 1. So we're going to get 3 to the power minus 1, which is actually just 1 over 3. So 1 over 3 times by 1 plus 2 over 3x, all to the power minus 1. So now we can do our binomial expansion with this expansion here. So we're going to use our formula. So our formula, remember, was as follows. So it was 1 plus n times by the value there, and then plus, I'll just write out the formula here. So 1 plus n times by our 2 over 3x in that. Just copying this thing there, and then plus n times by n minus 1 over 2 factorial times by this 2 over 3x, now all squared, and then plus ... the rest of the terms there. So if we sort this out then, so n is going to be minus 1, as we can see up there. So just plug that into the result. So a third times 1 plus, well, minus 1 times 2 over 3 is just going to be minus 2 over 3x. So n's minus 1. Minus 1 times by minus 2, because minus 1 take away 1 is minus 2. We're going to get positive 2 divided by 2 factorial. Well, that's just the number 1. And then 2 over 3 all squared. That's going to be a 4 over 9 times by x squared plus ... plus the rest of the terms. So we get 1/3. So expanding the brackets, 1/3 take away 2 over 9x plus 4 over 27 x squared plus ... and that's going to be our first expansion that we have. So let's just think about when this will be valid for. So when is our first expansion going to be valid for? So it's going to be valid for 2 over 3x, the modulus of this being less than 1. So remember this there, we want that term there to be less than 1, have an absolute value less than 1. So in other words, we want the modulus of x to be less than 3 over 2. Times both sides by 3 of this inequality, divide by 2, we get modulus of x less than 3 over 2. So that's when this expansion there is valid for. So that's expansion number 1. Now let's look at our second expansion, this one here, 1 minus 3x to the power of minus 1. Okay, so when is this expansion going to be valid for? Let's just move our writing up a little bit. So yeah, when will this one be valid? So we're going to do 1 minus 3x to the power minus 1. Now we've already got the 1 there, so we don't need to worry about like factoring out like the 2 that we did here, for example, because we've actually already got the the 3, I mean here, the 3, we don't need to worry about that because we've already got the 3. We've already got the 1 here, so we don't need to worry about that. We can just go straight to the formula. So it's going to be, again, using our formula, 1 plus n times by this term here, so negative 3x, and then plus n times n minus 1 divided by 2 factorial times by negative 3x squared plus ... the rest of our terms. So then again, we know that n is going to be equal to minus 1 again for this. So we get 1, so 1, and then minus 1 times minus 3 is a positive 3. So 1 plus 3x, and then minus 1 times minus 2 divided by 2 factorial, that's just a number 1, and then plus minus 3x x all squared, so plus a 9x squared there. And then plus dot, 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 the rest of our values after that. And when is this expansion going to be valid? Well, it's valid, so valid for the modulus of negative 3x being less than 1. Obviously, the modulus of negative 3 is literally just 3. So divide both sides by 3, you get a modulus of x less than a third. Okay, so now then, what we want to do then, if we go back to our question, is we're doing the expansion number 1 times 2 over 11 plus the expansion number 2 times 3 over 11. So now let's add our terms together. So I guess step number 4 is to just add everything together. So sum the 2 expansions. So step 4, sum both expansions. So we've got 2 over 11 times by our first one, which is 1/3, minus 2 over 9x, and then plus 4 over 27x squared, 4 over 27x squared, plus dot, 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 and then we want to add 3 over 11, so 3 over 11, because you obviously got 3 over 11 there, 2 over 11 there. So 3 over 11 times by this expansion down here. So 1 plus 3x plus 9x squared plus dot, dot, dot. Okay, so then when we tidy this all up, we're going to get, so with the first one, 2 over 11 times a third, that's going to be 2 over 33, minus 2 over 11 times by this value there, so minus 4 over 99x, and then plus this value there. Can't do that in my head, I'll use a calculator. So we're going to get plus 8 over 27 times 11, which is 297, lots of x squared, and then plus these terms here when we expand those, so 3 over 11, which is the same as 9 over 33. So I'm actually just going to write 9 over 33 there, just because we've got the 33 on the bottom there. And then plus 3 times by 3 over 11, so 9 over 11x, and then plus 27 over 11x squared, this bit there, and then plus dot, 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 the rest of these terms there and there afterwards, after that. Okay, so again, if we just tidy this up and simplify our result, what we get is we will get, so firstly, we're going to get 11 over 33, which is actually just going to be a third. So adding those 2 terms there, so 1/3, and then, okay, so minus 4 over 99 plus 9 over 11, lots of x, which is going to be 7 over 9x. So we get 7 over 9x. And then lastly, we've got 8 over 297x squared, in addition to 27 over 11x squared. That's going to give us plus 67 over 27x squared plus dot, dot, dot. So we've done the expansion. So what we can say, therefore, then, is that this expansion that we had at the start, so this 1 over, so 1 over the 2x plus 3, 1 over 2x plus 3 times by 1 minus 3x is approximately equal to what we just got here. So the approximation is going to be 1 over 3 plus 7 over 9x, 7 over 9x, and then plus 67 over 27, 67 over 27 x squared, approximately equal to that. But when is this true? So this is true when, well, let's go back to our expansions and when they were valid for. So we know that the first expansion was valid when the modulus of x was less than 3 over 2. So let's think about this on like a number line. So we've got a number line here, and I'll do this in blue. So the number line there, we've got 0 in the middle. So for the first expansion to be valid, well, we need the modulus of x to be less than 1.5. So let's just say, sorry, minus, 1.5, yeah. So between minus 1.5 and 1.5. So for expansion 1 to be valid, x must be between here. So this is the x number line. So expansion 1 I'll just call it exp1 is valid here. So expansion 1 valid in this range of x values here, because the size of x is less than 3/2. But how about the second expansion? So the second expansion is valid when x has an absolute value less than a third, so 0.3 recurring. So let's just do this in a different color. So a third, let's just say minus a third is there, 1/3 is there. So the second expansion is valid in this region here. So expansion 2 valid here. So that means that both expansions, when you add them together, are only going to be valid in the intersection between these regions. They're only going to be valid here. So both expansions together are going to be valid in this pink region. So that means that the sum of the expansions are valid when the modulus of x is less than a third, because we need both of them to be valid. So only both of them will be valid if the modulus of x is less than a third. So therefore, this approximation is only true when the modulus of x is less than 1/3. So that's going to be when this is valid for. So basically, this fraction here is approximately equal to this here. Obviously, you've got more terms going over here, but if we're just going to do the first 3 terms of the expansion, just like the question asked us. So the question asked us, show that it can be approximated in the form a plus bx plus cx squared. So we've done that here. So your a value would be 1/3, your b value 7/9, your c value 67/27. So these are our values, and this again, this fraction is approximately this fraction when the modulus of x is less than a third. So basically, you can use this approximation to approximate values of this result here, basically. So that's an example of how you can use partial fractions and also binomial expansion to approximate fractions in terms of expressions. And what you can do as an application of this, when we come on to differentiation and integration, you can actually approximate integrals and derivatives using this binomial expansion approximation, and that's an easier way of doing integration and differentiation rather than using that here. So you can actually use these approximations to make life a little bit easier for you, but the key thing is that this approximation is only going to be true in a certain region of validity, and in this case it's going to be when the modulus of x is less than a third. So that's an example of how we can use binomial expansion to approximate partial fractions.